Okay, so next what I want to do is I want to solve a differential equation y double prime. Last time we solved y double prime equals y. Now I'm interested in solving y double prime equals xy. This is an equation that is so hard it has someone's name attached to it. This is called an Airy differential equation. Certainly any solution that we find to this differential equation is not going to be particularly nice. It's not going to be able to be written in terms of elementary functions. But the starting points are going to be basically the same. So we're going to do the same process. We're going to assume that we have a power series for y centered at 0. So that's going to be a sum from 0 to infinity, c sub n x to the n. That means that y prime is going to be the sum from n equals 0 to infinity, n c sub n x to the n minus 1. Actually, I really want this sum to start at 1. And y double prime is going to be the sum from n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2. And so plugging all these in, we're going to see that we need to look at y double prime. So this is the sum from 2 to infinity, n times n minus 1, c sub n, x to the n minus 2, equals x times y. So this is the sum from 0 to infinity of c sub n x to the n. And we're going to need to do a few things here. So all the tricks that we've talked about in our study of these series solutions of differential equations, all of our tricks are going to come to bear, and we're going to have to do a few things. So the first and most obvious thing that we can do is we can actually, and I'm just going to slightly cheat here, but we can actually take this x, move it inside the sum, and what that's going to do is that's going to make this an x to the n plus 1. Okay. And the next thing that we're going to do is we're going to need to figure out how do we get the powers of x to be the same, and how do we get the starting indices to be the same. So right now the left sum starts with n equals 2, the right sum starts with n equals 0. We need to get them to be the same in order to equate them as power series. So what we're going to have to do is I'm going to look at the left sum, and I want to think about when n is equal to 2, what's our smallest power of x that we're going to get? So in other words, when n is 2, we're going to get x to the 0. Okay, so that's our smallest term there. On the right side, when n is equal to 0, so that's the smallest value of n that we have, the smallest term we're going to get is x to the 1. So what that means is that the left side is going to have an extra term that we don't have on the right side. So I'm going to peel off that extra term on the left. So this is just the n equals 2 term. So if n is equal to 2, we're going to get 2 times 1, c sub 2, x to the 0. So this will be 2 times 1, c sub 2, x to the 0. And I'm just going to take that out of the sum, and now we're going to have the same sum, but starting at n equals 3. So we just copy that. The right side is the same as it has been. So this is c sub n x to the n plus 1. This is an n, not a u. Okay, so x to the n plus 1. And then we're going to shift the index on the left sum. So that means that we're going to look at, on the our differential equation is going to take the form, so this is 2c2 plus, let's see, so over here we're going to have, if we shift our sum so that instead of starting at 3 we start at 0, that means that I'm going to have to change all the n's to n plus 3's. So n plus 3, n plus 3 minus 1 is n plus 2. This is going to be c sub n plus 3, x to the n plus 1. And now we've done it. We have our series with the same power of x, and with the same, so with our same power of x, and with the same starting index. Okay, so both starting at n equals 0. And now we're ready to equate these. Remember that we don't have any constant term on the right, so I can add a plus 0 there if I want, just to emphasize that it has to be the case that 2c2 is 0. So that tells us that, of course, C2 is 0. All right, and then this is a third degree recurrence, which is something new that we haven't seen yet. But this is going to work the same way. We're going to look at the terms in front of our powers of x in the series, so those sequences, and those are going to be equal for all values of n starting at our starting point n equals 0. So this means that we're going to have n plus 3 times n plus 2 times c sub n plus 3 is going to be equal to c sub n, and this is going to hold for all n, so for all n greater than or equal to 0. And so the first value of n that this is going to say something about on the left is c sub 3. So that means that we get to do what we want for the first few values. Actually, that's not completely true. We know C2 is 0. We don't get to do what we want with C2. C2 has to be 0. But we do get to do what we want with C0 and C1. So we'll call those A and B. And I'm going to rewrite our equation so that we got C sub n plus 3 is equal to C sub n over quantity n plus 3 times n plus 2. Okay, that's an n plus 2. And again, this is only true for n greater than or equal to 0. So now our job is to figure out this recurrence. And we're going to just have c sub 3, and that's going to be c0 over, let's see, if n is equal to 0, that's what we need to get this to be a c3. So if n is equal to 0, we're going to get 3 times 2. And c0 we called a. So it's going to be a over 6. I want to emphasize that I know ahead of time that this is only going to have a non-elementary solution. That means that we don't have to figure out a closed formula for the recurrence. There is going to be no closed formula for the recurrence. That's going to be nice for us. So I'm not going to bother to keep track of that. C4 is what we're going to get when we plug in n equals 1. So it's going to be C1 over 4 times 3. C1 we said was B, so that's B over 12. C5 is going to be C2 over 5 times 4, and that's 0, because C2 is 0. And then a few more values. C6 is going to be C3 over 6 times 5, and C3 we said was A over 6. So this is A over 6 times 1 over 30, so that's A over 180. And then let's just do one more, actually two more. C7 is going to be C4 over 7 times 6. C4 is B over 12. And so that's going to be divided still by 7 times 6. And then this is going to be B over something. This is where I would use your help as a class, because I'm really not good at multiplying. This is 12 times 42. Let's just do it here. I don't need to resort to using a calculator just yet. This is 42 times 12, so that's going to be 84 plus 420, so that's going to be 504. And then our final term, C8, is going to be C5 over 8 times 7, which is 0. Okay. Now what we're ready to do is we're going to take all of our terms that we have, and we're going to put them in a power series. Remember that our power series, y, we write it as a series for convenience, but that really hides what's going on. This is the series, C0 plus C1x plus C2x squared, C3x cubed, C4x to the fourth, and so on. So what I want to do is I want to write all the terms in the power series up to, say, the C8 term is 0, so say up to C7. So this is going to be C0, which we said is A, plus C1x, which we said was, C1 was B, C2 is 0. So just for now, just to keep track, I'm going to write that in. C3 we said was a over 6. So that's a over 6 x cubed. C4 we said was b over 12. So that's b over 12 x to the 4th. And then a few more, plus C5 x to the 5th, so that's 0 x to the 5th. C6 times x to the 6th is a over 180 times x to the 6th. And finally, C7, which was b over 504, x to the 7. And then we would have infinitely many more terms. I'm just writing the first few. And so what I want to do is first just notice that the x squared, x to the 5th, x to the 8th terms all cancel. Right? Those are all multiples of 3 plus 2. Those terms all cancel. And so all we're left with are the powers of x, where the powers are multiples of 3 or multiples of 3 plus 1. So this is kind of like the even and odd situation that we had, where we had a different one if we have a multiple of 3 plus 1 or a multiple of 3. And so what I'm going to do is I'm going to group our power series together. So I'm going to take all the terms that have an a in them and write that first. So this is going to be a plus a over 6x cubed plus a over 180 x to the 6th, and so on. I don't have any more terms there, but then the b terms are going to be bx plus b over 12 x to the 4th plus b over 504 x to the 7th, and so on. And then the final thing we can do is we can factor out the a and the b from our series. So this is a times 1 plus 1 over 6x cubed plus 1 over 180 x to the 6th, and so on. And b times x plus 1 over 12 x to the 4th plus 1 over 504 x to the 7th, and so on. And so these are going to be our two linearly independent solutions, right? Our y1 and y2. These are not solutions. y1 and y2 are not functions that we would recognize outside of, these are not functions that we would recognize outside of a power series. There's not elementary representations for these functions, but we're done. This is the best that we can do. Okay, so we're done.